This is 14.6, the Doppler Effect. You've probably heard of this before.
Like Doppler radar.
Like Doppler radar. So we're going to describe how frequency affects velocity and how to calculate this Doppler effect. So first of all, frequency. Stationary frequency is normal. It's just, frequency is hertz, so that's 1/2, so it's cycles per second. If it's a very fast wave, it's going to have a very large number because you're doing, like 100 waves in 1 second. Whereas if it's decimal, then you're only doing a portion of the wave that second. Since it's stationary, it means that you hear it at the same frequency that it's being emitted, which kind of seems obvious. Like, if you sing a C, if I'm standing still and you're standing still, I'm going to hear a C. So when stationary, both the object and the observer are not moving, so the frequency remains the same. Yes?
If you yell louder, the sound coming out.
No. It's an interesting question, but it only increases the size of the wave. O'Brien?
Sure.
All right, so the Doppler effect. Basically, it states that when an object or an observer is moving, it's going to stretch the wave, and it'll either stretch it or compact it, depending on how everything else is moving. This makes the frequency change. So the wavelength is changing, and the frequency is changing. So when objects are getting closer, you actually hear a higher note. Imagine that you're in a car and an ambulance is coming up behind you. You hear the note really high, and then it passes you, and then it goes really low. Right? And so when they get further apart, it drops down to a lower note, a lower frequency, so the wave is stretched. So when it comes at you, the waves build up. They're compacted, which makes it a higher frequency and a shorter wavelength. And then when it goes away from you, it's a longer wavelength. So it goes a lower frequency, making it a lower note. Okay, so here is what a stationary object looks like. By the way, I pulled these off of Wikipedia. I thought they were the coolest things. I found them in my first year of teaching. I was like, this is awesome. And I was actually able to embed them in my PowerPoints, so I didn't drop these. Okay, so this is a stationary one. You can see that the wave fronts are all evenly spaced out, so everything's fine. Now let's look at something that's moving. You can see in the front they start to bunch up, and in the back they actually are spread out. So there's a higher frequency up here and a lower frequency back there.
Like, that's how I feel it would look like going through a wormhole.
Okay.
Or the White Rabbit's hole. I don't know.
Yeah, if you play in reverse, it kind of looks like the double.
Okay, now this one is a sonic boom. So it's going as fast as the speed of sound, 343. You can see it's like riding the waves. So it makes that big pop noise when it comes to your ear. Or you can do it when you crack a whip. Just pop.
Okay, wait.
Break the
Isn't it
sound
a
barrier when you crack the whip.
Yeah.
Wait, when you crack a whip, doesn't the sound come from the very end instead of all the way through?
Yeah.
So wouldn't that mean that's not like cracking a whip?
The end part of it is moving that fast to crack it. So no, not the whole width is not doing that, but the last little part pops it. But it's a change in direction to get it to go, because you have to have the flip. All right, and this one is going at supersonic. You can see it's actually traveling faster than the speed of sound here. So it's in front of the sound wave that it's creating.
Okay. That's cool. I have a question. I thought that nothing could actually go faster than the speed of light, and that if you did, you'd have to like time travel in front of it, like into the future.
Well, there's different theories on that, but so far we can't go faster than the speed of light, so that we know of.
Okay.
Light is sort of faster than sound.
Yes. So this is speed of sound.
Okay.
Much, much slower.
Okay.
Right. The speed of sound is only 343 meters per second. The speed of light is like 3 million meters per second. All right, so Doppler effect. Here's a, not moving thing so you can look at it. You can see how these ones are longer. So when the object is moving that way, they are spread out on this side and bunched up on this side. So this will be your source. S is source here. And then you have your observer A, higher frequency, and observer B is going to see a lower frequency. So here's your equation. When I taught this out of the honors book, it was like the hardest thing to decode. And every book tends to be a little tiny bit different. So here's what I've been able to figure out. Because your book tries to talk about like the directions of the velocity. So if the velocity is moving left, it's negative, and right, it's positive. But then you have to figure out how the source is moving versus the observer, and which makes it kind of confusing. So here's what I do instead. I say that they're negatives. And it's positive if the detector and the source are getting closer together. So you change this one to positive. So if they're closer together, this is negative and this one's positive. And then if they're getting further apart, then this one's positive and this one's negative. F naught is this is what the observer is seeing. And Fs, this is the source. So whatever's making that sound, or whatever's traveling with that sound. And V is the velocity of the sound, 340 or 343, depending on how accurate you want to be. So this will be the velocity of the observer and the velocity of the source. Actually, we could probably do an interesting experiment. I have a sonic gun type thing, like one of those air cannons, and it makes a noise when you do it. So I was thinking maybe you guys can run with it and let's see how the sound changes as it's running. I don't know if it's like a long enough sound to make it work. You can do them with those Nerf footballs with the whistler stuff. You throw it past your head, you hear it the high to low. I just don't have any.
We'll figure it out.
What if
We
you
just run with that.
Darn it! I'm gonna make that pun.
All right, are we ready? We're good? All right, let's practice this Doppler effect. You are in a car going 15 meters per second, and the ambulance comes up behind you at 25 meters per second. If its siren emits a frequency of 950 hertz. What frequency do you hear as it approaches? What frequency do you hear after it passes? And what frequency does the ambulance driver hear it? So they have 15 meters per second, 25 meters per second, and 950 hertz. What is this 15 meters per second?
Is that the
Observer's velocity. So VO. And what's the 25 meters per second?
is the
yes.
sources.
Good. Source's velocity. And what's the 950 hertz?
The frequency source.
Frequency of the source. So we're looking for a frequency observed here. One of them is when it is coming towards it. So as it approaches, as it goes away, and then we want to know what does the ambulance driver hear it. So what frequency does the ambulance driver hear it? Okay, so the first one, FO, FS, V, minus, V, what's the equation again? O, and S. There we go. All right. And this one's plus if towards, and this is plus if away. Oh, go back. No, really. Plus if towards. Okay. So part A, FO, 950, 340, 340. And are we getting closer or further away?
Closer.
Closer. So
Whoa.
positive, negative.
Where did the 340 come from?
That's the speed of sound right there at the very bottom where it says V is 340.
I did
Or
not see
343 to be more. Okay, 15 for the observer and 25 for the source. And we have 1071 hertz. All right, so that is the frequency. Does it make sense that he's hearing a higher frequency? Yes. Yes, because they're going towards. So you just want to make sure that these things are making sense. Okay, for the away, same stuff, but you're going to flip the signs here. Which, if you have one of these calculators, you can just go back and change your plus and minus. That's what I'm going to do. Sounds super lazy. And I get 846 hertz. And does it make sense that it's lower?
Yes.
Yes, because they're going away. So further apart should be a lower note. All right, next. C. What
950.
frequency does the ambulance driver hear?
950.
950. Why?
Because they're going the same speed in the same direction.
Same speed, same direction, so the frequency is 950.
And they're only going in one direction.
Here you go. All right. Questions on this?
This is surprisingly simple. What's the catch?
Wait, same. I'm convenient just because
The ambulance driver is traveling at the same speed as the siren. So
And
if you think about his frame as reference, everything else around them is moving, but they are not. It's not moving relative to the driver.
And they're going in one direction.
All right, let's try my clicker question. Since I clicked to it before, it might not work again, but we'll try it. We'll see if it happens. If it doesn't work, then I'll do something different. All right. A train station bell gives off a fundamental tone of 500 hertz. Now, fundamental is like just its frequency. Don't worry about the fundamental part. We'll talk more about that tomorrow. As the train approaches the station at a speed of 20 meters per second. If the speed of sound in air is 335 meters per second, what will be the apparent frequency of the bell to an observer riding the train?
Wait.
So there's a train bell on the station. The bell is at the station. And the people on the train are traveling towards the bell at 20 meters per second. And the bell itself is not moving.
Right.